Hi everybody, and welcome to Lecture 6 of the Digital VLSI Design course at Bar-Ilan University. I'm Dr. Adam Teman, and today we'll start moving to the physical domain of the VLSI design process. So what's next? We've basically finished the front end of the design process, and we'll now start the back end of the design. So the front end was this part over here, where we basically defined all the logic and how we're going to build our chip and how it's going to fit together. And now we'll move to this part, which we often call the back end. The reason it would be called the back end is because it's more associated with making the metal layers, I guess, or the connections between the different cells, which is done at the back end of the line in the design process. Versus beforehand, we defined our logic, which is associated with the transistors, which are made at the front end of the line. Okay, so to start, we'll move between tools with a logical approach to ones with a physical approach. Then we'll make a physical foundation for our design. So the first thing we do is we'll draw up a floor plan. This will include making what we call big decisions or important pieces. We'll decide where they are, such as the IPs that we have, the different input-output circuits, the power grids, the special routes, and etc. After that, we can go and we can place our gates. When we say placement, we're talking about placing the whole sea of standard cells, the whole set of these Lego pieces that we have in a big box, different AND gates and NAND gates and so forth. And when we do that, we have to take into consideration two things: congestion and timing. When we finish our placement, now we have put our flip-flop somewhere. So now we know where our clocked elements are. So then we can go on and build a clock tree, see how we distribute the clock to every part of the design. Finally, we can route our nets or do detailed route, where we actually go and connect all of the nets to all of the pins in the different gates and IPs. We have to take into account DRCs, our design rules, and of course timing, noise, and other things. Finally, before tape out, we'll clean up things, we'll verify, we'll make sure everything is connected and that we are breaking no rules. So illustratively, we can look at this as such. So our first step is we're going to move to a place and route tool, or P&R tool, and that will contain an initial floor plan, like what size our chip is, how our pad ring is made. These things are the pad ring, and for example, where our core area where we have our standard cell rows are. Then we'll go on to power planning. We may build some rings of VDD and ground for a good distribution of the power around the chip, and bring some stripes of power to bring power and ground a lot better into the standard cells themselves. Next, we'll go into our placement. Well, we'll actually place the standard cells in the floor plan, the core area. Once we have our design placed, we have to see where our different flip-flops are, our clocked elements, and then we can go out and build clock trees, which these things would be the buffers that we added during clock tree synthesis. Okay, now that we have all of our elements basically in place, we can go on to what we call detailed route, where we actually go and connect nets to every single part. And finally, we can prepare the tape out, we can add the filler cells, we can do all kinds of other things, do checks and so forth, and be ready to go. And what we'll get in the end is something that looks similar to this picture over here. So, looking at that from a higher level, I guess, perspective, we can look at what we need for moving from the logical to the physical design. We have to define our design. That's usually a .v, a Verilog file. We have some sort of a Verilog netlist that came out of our synthesis. We also have our SDC constraints, basically the same SDC constraints. There may be several modifications, but they're basically the same SDC constraints as we had during synthesis, which tell our tools what our optimization goals are. We have to define our operating conditions and operating modes. That's MMMC, and we learned all about that. Okay, and we now are going into the physical world, so we have to have technologies and libraries such as LEF files. Okay, finally we take our whole set of inputs and we define a floor plan, or the area that we want to put our stuff into and what it's going to basically look like. And now we can go into what's called the physical design flow. Once we finish the physical design flow, we'll get a detailed layout exported as a GDS2 file. So, during synthesis, our worldview was a bit idealistic. We didn't care about power supplies. We just knew that there was some sort of VDD and ground, or 1 and 0, but we didn't really care about where the power was and how it gets everywhere. And you can see here on the side there's a more complex chip, that there are different parts of the chip with different power domains and so forth. Maybe even the power is turned off in one of them. So this is much more complex than we did up till now. We didn't care about physical connections or entities. We didn't care about clock non-idealities. We always put that delta skew as 0 and that delta jitter and so forth as 0, right? Therefore, in order to start physical implementation, what we have to do is we have to define our global nets, that say what VDD is, how it actually connects to each one of the cells and so forth. Each one of these parts we'll discuss later on. Okay, we have to provide technology rules and cell abstracts. So we have to tell it what the DRC rules are and what the left files that include like the size of our cells, where the actual pins are and so forth. We have to provide physical cells. These things were unnecessary when we were doing logic functionality, such as filler cells that just filled up the empty area of the floor plan, or tie cells that tie gates to 1 or 0 constants and so forth. We have to define hold constraints in all operating modes and condition. This we saw we do with MMMC. But we could have used MMMC already during synthesis, but hold was very easy to meet. We had an ideal clock. We didn't really check it. We only checked setup. Now we have to do hold as well. And we have all kinds of things like low power definitions, such as voltage domains, power gates, body taps, etc. This is a bit outside the context of this course, but it is something that we have to do when we move to the physical domain. So having discussed a bit about this low power design stuff, let's go a bit deeper into multiple voltage domains just to get a feel for it. So we have a multiple domain design. We have this floor plan here, and here's the basic core area, but what we decided to do is make several power domains. So what we should first do is create power domain names and a list of cells connected to them and where they are physically. So this would be power domain 1, power domain 2, power domain 3, and we'd have to tell the tool each and every cell which power domain it's associated with. Then we have to place macros. We have to remember that, say, this RAM sits in power domain 1, we better put it in the area where power domain 1 is, and same with this ROM in power domain 2. This IP would be in power domain 3, so let's make sure we place it there. We have to really take into account things such as routing congestion and orientation. Usually it's best to do this manually rather than auto. Okay, and finally we have to place switches. Sometimes we'll have these power gating switches, which I'll discuss in a minute, so we should put them around our power domains that may have retention. Level shifters. We may have a power domain scheme such as this. So we have this domain which works at 0.7 volts, and this domain works at 0.9 volts. This domain is really complex. We can power it at 0.7 volts or at 1.08 volts, or maybe even move in between them. That makes our life a bit more complex than usual. So we have this 0.9 volt domain, and we have an 0.7 volt domain, and we have to have a level shifter that pushes data from one domain to another. And same with an 0.7 volt domain to an 0.9 volt domain. The things get really tricky when we have these types of domains that can, so if we go from 0.7 volts to 0.9 volts, it would be an upshift, versus if we go from 0.9 to 1.08, the upshift would be in the other direction. So we have to take care of all of this. We'd have a logic model for these types of buffers that sit in between the domains, or actually connect between the domains, where we'd have something like it'd be a buffer, so there'd be these two inverters where the input of one would be one VDD and the output would be a different VDD. And let's see how we can do that. So actually, when we're just driving down, so if we're going from 0.9 volts to 0.7 volts, we can generally just use a regular CMOS inverter and everything will work well. The problem is when we need to drive the voltage up, such as 0.7 to 0.9 volts, or we need to take care of both ways. Sometimes this will be a downshift and sometimes this will be an upshift. So the basic looking circuit to do it is what we call a DCVSL type of a logic gate. So this type of a buffer, it makes sure to pull up to the high VDD when we're doing a voltage rise. This can also take care of the voltage low. Actually, these types of gates, they have have one main voltage, the VDD high, which would be usually in this case VDD2, the inverters at the input, they may work on the low VDD, so they might need to have a second VDD. But we're going to have to stick this into these standard cell rows, and often these will be a double row or triple row, as we can see here, and that's okay. If we have a special site that takes care of it, the place and route tool will know how to deal with it. But what we have to notice is that we'll only have in a certain area of standard cell rows a single VDD, either the VDD1 or the VDD2. In this case, we have VDD1 all over here. So what that means is that when we take VDD2 into the cell, we have to input it as a signal pin. That's called secondary power routing, and it has to be taken care of, and it's very non-trivial, especially for IR drop and so forth on these types of voltages. So this is quite complex, and I won't go into any more detail about it now. Another point about multiple voltage domain design is power gating. So sometimes we want to turn off a block so to lower leakage when we're not using it. So this can either be done with a header switch or with the footer switch. We just put basically a single transistor that gets some sort of a control that closes off the path from VDD to ground, and it makes leakage much lower. Well, there is of course a question here: how big does this switch have to be? And it has to be really big, because we don't want it to be some sort of resistance or significant resistance on the path to our standard gates inside. So how do we do this? Well, we have to have some sort of stripes of VDD, say, that go into some sort of switches, and then we'll have like our ground, which if we're talking about a header type switch, this would be a header switch, and it powers these rails that actually feed the cells themselves. So how are we going to do that? There are several ways. The two primary approaches are to do it in this outer gated style, where we'll put the switches. These are all switches that are parallel to each other. We'll put them around the domains, and that's really nice from a floor plan type of a concept, because we can just do our regular old place and route inside the different domains, and we just have to treat the switches outside and route their signals to them outside the actual floor plan of this part. But it means that we have a longer way to go from each of these switches until we get to the actual gates. So it would be much better if we could interleave these switches inside the domains themselves, and that's another way of doing it. It just makes the whole floor planning a bit harder. So how do you define all of that? Well, we're not going to discuss it now. We'll leave it to a different course. But in general, there's a command format for this, or, well, there are actually two command formats for this. One of the command formats is called CPF, or Common Power Format. That's Cadence's proprietary format, and it's surprisingly, actually kind of confusingly, similar to MMMC. So if you get used to using MMMC, it's not that hard to go to CPF once you learn and get the hang of it and understand what each of the commands are for. However, Synopsys has their own type of a unified power format, or UPF, which is their way of making it common or unified. It's very similar to SDC, so if you like SDC, then you'll probably get more used to UPF. There are several intricacies, differences between CPF and UPF. Again, I'm not going to go into them here in this course. UPF has recently been standardized by the IEEE, so maybe it's actually winning the fight, though CPF is still fully supported by Cadence tools, as is UPF. I guess neither of them is either common or unified. So luckily for you, we're not going to talk about this anymore right now. Instead, we'll start with the basics of floor planning. So let's start to talk about floor planning. What are the goals and objectives of floor planning? So floor planning is basically a mapping between the logical description, the netlist, and the physical description, the floor plan. Okay, what are our goals of floor planning? We want to arrange all the blocks on a chip. We want to decide on the location of the I/O pads. We want to decide on the location and the number of the power pads. We want to decide on the type of power distribution. We want to decide on the location and type of the clock distribution. So those are our goals for floor planning, and we'll discuss each of these things in future slides in the course. The objectives, okay, so the objectives are obviously we want to get to as small a chip area as possible to make our design as cheap as possible. But we also want to meet our timing constraints, so we want to minimize delay, and we can only do this if we minimize routing congestion, or else we won't be able to finish our detailed route. So let's give a general kind of look at our design, and we can see a typical type of design. Again, this is a type of a periphery or I/O area. These I/Os, they're really big. They're these types of buffers, and we'll discuss them in a later course. We'll go deep into them, see how they're built and so forth in a later part of the course, but they're really big. As you see, I mean, this is not maybe to scale for most chips, but these things are huge, and so we usually put them in the periphery of the chip, and they have a big space that you can see pretty well and differentiate from the rest. Then we'll often make these rings around the inside, so these I/Os which bring in the power can connect to these rings, bring them power, and then distribute the power either by these rails over here that are VDD and ground, or by stripes that help us bring VDD and ground closer to the rails which actually connect to the cells. We have to have our different blocks inside, these IPs, RAMs, ROMs, etc., and we have to make sure that our power grid actually nicely connects to these guys to give them power as well. So when we talk about the floor plan, we have to take into account the chip size, the number of gates, the number of metal layers, the interface to the outside, the hard IPs and the macros, the power delivery, if we have multiple voltages, how we're going to clock the thing, and do we implement our chip in a flat or a hierarchical fashion. And we'll discuss all of this in the coming slides. What are the inputs and outputs to the floor plan? Okay, so we have to have, obviously, a design netlist. That's what tells us where our gates are, what types of gates we have to place inside. It tells us how many gates we have, etc. The area requirements, we have to know what size we have to make the chip. Now that can be driven by our netlist, by how many gates and what the gate composition is, but it also can be driven by the system where we know what our package is going to look like and how much room we have to actually implement this block or this chip, and so they will tell us what the size, what the features of the area are, and so forth. What our power requirements are, how much current we're going to be dissipating, what type of IR drop we can tolerate, and so forth, and we'll discuss that a bit later. What our timing constraints are, so that's our SDC file basically. Physical partitioning information, that's if we divide our whole design into subblocks and we use a hierarchical flow to deal with them separately and make our problem a bit smaller. We have to have trade-offs between die size, performance, and schedule of actually making the tape out. I/O placement, well, if we're talking about a whole chip, we're going to have to put those I/Os, and usually the I/Os will have to be put where they should fit on the board or in the package. But sometimes we're going to be talking about a smaller block, and we just have to discuss where to put the pins that actually let us get in and out of the block that we're dealing with. Macro placement information, this is a good question, and we'll discuss in a few moments how we decide where to place our macros. So those are basically the inputs to our floor planning. What are the outputs? Well, we get the whole area of our die or of our block that we're implementing. We know where the I/Os are exactly. We know where the macros are exactly. We have defined a power grid, and we know what it looks like. We have pre-routed some the power routes, and we know what our standard cell placement areas are. And if we want to, we can define all kinds of things in that. So let's discuss how we do this kind of more particularly. At this point, the design is ready for standard cell placement, and we can apply our placement algorithms that we'll discuss in the next lecture. So just an I/O ring. As we saw before, the I/Os are often put in a ring around the chip. At least they were when we discussed what we call wire bond design, which we'll discuss in a later lecture. But in general, usually we talk about an I/O ring that lets us actually drive the voltage of the I/Os, which is often higher than the voltage of the core, in a ring, and distribute things around the chip and so forth, and be able to hook up to our package in a more short and better way. Okay, so the pin out is often decided by the front-end designers. We know from whoever is making our the higher level, which could be the system or whatever, we know where we know that from this side we want to have our DDR pins, and from this side maybe our Ethernet comes in or something like that, and that's why we'd put our different I/O pads on in certain places. Okay. The problem is that I/Os do not scale with Moore's law. Again, we have some sort of machine that has to do this wire bond, that has to actually connect this pin to the chip. This pin is already much bigger than our wires that are inside the chip. They don't scale very well. The machinery hasn't gotten that much more fancy in the last 50 years, and so these things stay big. They have high capacitance. They have high inductance, and we have to make sure that they're also driven into and out of the chip in a very fine fashion, as we'll learn later. So we use these pins for both connecting signals, data signals that go into and out of the chip, but it's also for providing power to the chip. So it's a very critical and very central stage in floor planning the chip. We'll leave it for a bit and revisit the IOs a bit later. But there is a question of how do we choose the size of our chip? Well, let's look at this type of a chip, and we see that we have these IOs around, and we have a lot of logic. In fact, it looks like, maybe we won't have enough room, and we'll actually want to make our chip a bit bigger. This type of a chip, which is kind of the classic thing we looked at when at the very early stages of Moore's Law, is what we know as a core-limited chip, because our core is very big. We have a lot of logic in here, and in fact, if we'd make the chip a bit bigger, we'd have room for more IOs, and maybe we wouldn't even have anything to do with them. The reality is that often nowadays, chips are actually what they look a bit like this. We have a lot of these IOs. We have so many connections to things that are outside our chip that we have all this wasted area inside that we don't actually use for placement. We can do our whole placement in a much smaller area. So this is all wasted real estate. This type of a chip is called a pad-limited chip, and that's often the case. So you need to make sure that you understand that each one of these guys is very expensive, and if we add too many of these interfaces, we're going to actually become pad-limited, which means we're wasting a lot of area that we're paying for, but we're not getting much out of. Utilization. Utilization refers to the percentage of the core area that is taken up by standard cells. So if we look at this picture of a placement over here, we see that there are all these blue things. They're standard cells, but there's a lot of black area, like this whole black area. You see there's nothing there. That means we're not utilizing that area. So utilization is the percentage of the area, of the core area, that is used by standard cells. And this is a low standard cell utilization. There's a lot of this black area. A starting utilization might be 70%. Why are we going to want to be leaving this type of area? Because, first of all, we may have all kinds of buffering and so forth to add and resizing, but we also need it for routing congestion. So high utilization can make it difficult to close a design. Look, this is a really high utilized area. There's not much black in here. There's not much room to change the sizes of certain cells to upsize them. There's not much room to actually do all kinds of very tight routing. So high utilization can make it really difficult, and it means that when we do optimization at later stages of the design, we may have to do all kinds of strange things like route around or do all kinds of things, put some sort of buffer that we want to add. Instead of putting that buffer over here, we might have to stick it over here and send our route over to here and back, and then it actually gives us a much worse, or at least a much different influence than we thought. So local congestion, and congestion is what is discussing the routing congestion. It can occur with pin-dense cells like multiplexers. So if we take, for example, an inverter, if you see there's an inverter cell, right, it has some sort of input and output. So there would be a pin connection here and a pin connection there, and I'd have to bring some sort of a route over to the first pin and a route from the second pin. But a mux, if we were to take a mux, right, what we have here is we have 1, 2 inputs and a selector and an output. That's maybe in the same type of size cell. We would now have 4 of these connectors. In fact, if we'd have a 4 input mux, we'd have 4 of those, we'd have 2 of those, and 1 of those. We'd have 7 pins on maybe a small area, and we have to bring routes around that have to connect to all of these, and that causes a lot of congestion. So in things that have multiplexers, we're going to have a lot of local congestion, and we may want to make the placement less dense or the utilization lower in that area. We can run something called a trial route. That will give a kind of an estimation of what our routing congestion is. We can see that where we expect to have congestion and make changes in the floor plan according to the things that we'll see in the next few slides. Another point that I want to discuss is uniquification. So I don't know if uniquify is a real word or not, but in our field it surely is a real word. And uniquify comes from the word unique. We need to have our net list become unique. So a unique net list means that each submodule is referenced only once Now that's very strange because when we write our Verilog, we write something like this. We write module, and I call it B module, and we have two instantiations here of a module called A module. M1 and M2 are two instantiations of this. And it's really important to write hierarchically because that's how we can use design reuse, make our code more readable, and so forth. What we get here is this B module that we see here, and it has two instantiations of A module. One of them we called it M1, one of them we called it M2. And since A module, it just has a buffer called U1, we get this U1 buffer inside each of these modules. That is what's called a non-unique netlist. You see, each submodule has to be referenced once. Here we reference the submodule twice. We reference A module twice. We need to uniquify the netlist. To uniquify the netlist is to do something that looks kind of dumb. What we do is we take this module and we give it a submodule name, and this module give it a submodule name. So we have our same type of B module, but instead of referencing A module twice, we reference A module 1 and A module 2, and then we make a copy of A module, one that's called A module 1 and one that's called A module 2. We just copy it twice. So each of these instantiations has a one-to-one mapping to a submodule. Now, why would we do that? Well, this is for a very simple reason. Let's say we did our place and route, and now we start doing optimization. And for example, we have some sort of timing path that goes through this and some sort of timing path that goes through that. Now, we decided with our timing that we need to make this buffer bigger in order to meet the timing that goes through here. If we do it on our netlist over here, we make this buffer bigger, we'll also make this buffer bigger because we just have one module in the world. When we uniquify, now we can make this buffer bigger without touching this buffer. And that's very important. That's why we need to uniquify our netlist before placement can begin. Usually this is done actually inside the synthesis tool, so most netlists that actually reach place and route are done in are unique already, but we have to check this, and usually our place and route tool can uniquify it if it's not uniquified already. Okay, so let's discuss hard macro placement. When placing large macros, we must consider the impacts on routing, timing, and power. We usually want to push them to the sides of the floor plan. As you can see here, we took our macros and we pushed them to the sides of our floor plan. Why are we going to do this? Well, placement algorithms like a big, large area that they can play with, as square as possible and without any corners. For example, if we take this area here, we have this macro, and it is pushed to the side, but still there's this corner. And if we have a standard cell over here and another over here, and they have to connect to each other, they can connect like this, but it'll be hard for them to connect like this because they'll have to route over the macro over here. So this is a type of an area where we could have a congestion hotspot. The same would be true if we have these macros over here, and of course in between them there aren't a lot of routing tracks, so we want to make sure that nothing's put over there. But even on the sides it may be problematic. What we want to do is we want to push the macros all the way to the sides, make sure we don't have that many of these sharp corners, and make sure that if we do, we make sure that things aren't placed around them. After we've placed the macros, we want to mark them as fixed, so nothing will move them, nothing will make them change from our initial floor planning. We have something called placement regions. Well, usually the placement algorithms, as we'll learn, are pretty good, but sometimes things happen that are strange. Often it's because of garbage in equals garbage out. So we did something wrong that we didn't pay attention to, and if we're experienced designers, maybe we'll be able to see it. But often we can't, and we want to kind of help the tool. So we've taken the tool and highlighted different areas of different modules inside, and we see something very strange. You see this purple module? It's placed over here, but there's a little bit over here in these islands that are scattered around, and some of it's over here. That does not look too nice. This picture, on the other hand, looks a lot nicer. We have our whole purple module is completely over here. Considering that the cells and modules are mainly talking to each other with local route, that looks a lot better. So how do we do this? Well, we can do it with what we call placement regions. There are several types of placement regions. One is called a soft guide. That's the lowest level, which is, it tells the tool, listen, try and cluster these cells together without a defined area. It's kind of a strange type of a definition, but it does affect the algorithms that run these things a bit. Okay, we can give it a guide. A guide is a bit better. We can define a region and say, listen, this is your region. Try to place these cells inside this region, but you don't have to. A region is a bit harder concept. It says, listen, this is your region. All of these purple cells must be in the region or else it's a fault. And finally, we have a fence. That's even worse. It says, listen, all of the purple cells are in this region and no green cell can sit in this region. It's only for purple cells. Okay, so that's another type of a placement region. I just want to mention something. Usually this is not a good practice. We don't usually want to or have to go into the algorithm and change what happens if we know what we're doing. So you can tell from this type of a picture, we can see something like this. Usually this purple stuff would be over here probably because of two things. Either these RAMs, these are probably RAMs, these hard macros are part of the purple module, and then they pull the purple cells to be close to it. Maybe some of these IOs also are purple, so they pull these cells to be close to the IOs. On the other hand, probably these IOs, they talk directly to these purple areas, so they pull these cells over to here. I imagine that these little islands, they're kind of places that help us buffer and talk between these regions that probably have several paths that move together. And maybe these guys, some of these RAMs maybe are also part of the purple region. So it would be better to fix our floor plan if possible than to actually region out and make the tool do something that may be suboptimal. Placement blockages and halos. So we often call placement blockage a halo. That's an area that we put around a macro. So take this RAM, which is not placed at the side of the floor plan, so don't take it as a good example. And what we have here is we have the pins that connect to the RAM. So you see there are all these pins, and usually what happens is we need to route a lot of routes to connect to these pins. Well, if we have standard cells that are sitting here in front of these pin connections, that wouldn't be good because they'd be blocking our routes from going in, possibly even causing shorts. So what we almost always do is we'll put some placement blockage on the area right in front of the pins, maybe even on all sides of the macro. These are called halos because usually they're 360 degrees around it. We can define several types of placement blockages. There are other reasons to make placement blockages. So we can have hard blockages. That means that no cell can be placed inside these areas. We can have soft blockages, which means that, listen, no standard cell placement will be done inside, but once we do optimization and we need to add some sort of a repeater or buffer or something, then we can use this area. We have partial blockage. That means, listen, we know that the module that's going to be put here, it has a lot of those multiplexers which are really dense, and so we know that we don't want to have that 70% utilization here. Let's do this 50% utilization. So we can mark this area, say, listen, partial placement blockage, only give 50% utilization inside that area. And we have these halos, which, as I said, they're what's around these RAMs and stuff. They're a keep away area for standard cells. So hard blockages we'll usually put on all sides of these RAMs and so forth. But when we put the RAM or the IO next to the corner or next to the side, what we're usually going to want to do is put soft blockage between the cell and the sides of the macro or the floor plan. And the reason being that the placement tool will often not understand, and it will put standard cells here that then need to be routed to their friends who are outside. That's really bad. So we just put a soft blockage here. If we need for some reason a buffer that just needs to strengthen a signal, it can be used, but that will only be done during optimization. We also have routing blockages. They may be less commonly used, but for example here we decided that we don't want anything routed in this area, so we can put routing blockage over here. Usually we do that per layer, so it might be in a certain layer we don't want any routing to be implemented, but that's a less commonly used type of a blockage. So to summarize all that, we have some guidelines for a good floor plan. Okay, so this is our floor plan, and we can see a bunch of things. So first of all, as I said, our placement algorithms, they like the single large cell area. Here they can run their algorithm really nicely, as we'll learn in the next lecture, and we can get a really good solution if we have this large core area that's uninterrupted. Okay, we want to take our RAMs or our IOs, our IPs, we want to put them outside in the corner far away so they don't obstruct this standard cell area. we want to have large routing channels. So let's say we have the PLL over here, it needs to route to here, it's not going to maybe go over the RAM. So we want to just make sure that there's a lot of room in between so we don't have a bottleneck over here that's going to cause all kinds of routing congestion. Okay, and we want to take the pins of so we have this block, we would rather put it in the corner where there are no pins in the corners, because if there are pins in the corners, then we have to get a lot of routes that come over to here. We may be pulling standard cells over there and so forth, so try to keep the pins out of the corners. Looking at this other example, we have this RAM over here. It's not very nice because we have a lot of pins that are right adjacent to the side of the floor plan. So if we could rotate this by 90 degrees. Nowadays that's not usually allowed for things such as SRAM. Usually the poly have to be in the same direction, so we're not usually allowed to do these 90-degree rotations, but in older design technologies that was we were able to do that. But try to keep these pins away from the sides. Okay, and we also don't want to have these constructive channels. So these areas, if a standard cell over here has to talk to a standard cell over there, they're going to have to go through this channel, and ones over here talk to ones over here are going to have to go through this channel. It's going to cause a lot of routing congestion. Try to stay away from those types of constructive channels. Another thing is that, again, we have the pins over here. We should use blockages like the halos over here to allow a lot of access to the pins without being disrupted by all kinds of standard cells that are placed there. So I just want to discuss for really a couple of minutes about hierarchical design, or how we deal with a really big chip. So there's a question of flat versus hierarchical design, which I brought up before. If the design is too big, what we're going to do is we're going to partition it into hierarchies. So we take the full chip design and we decide that the netlist should be broken up into different, basically, modules or blocks, and each one of them we're going to do a place and route flow separately. So we have block 1, we do a place and route to block flow, 2 a place and route flow, block 3 a place and route flow. We close these designs separately, and then we connect them all together for full chip timing and verification. So the advantages are very clear. We get a faster runtime. To do the place and route flow of this partition is much faster than doing the whole chip at once. We need less memory for EDA tools. We need less runtime. In fact, we need fewer licenses. Okay, if we need to make an ECO, an engineering change order, the turnaround time is much faster to do it on a smaller block than doing it on the whole chip over again. And we can do design reuse. So if we did this place and route flow on this block, we can take this block as is and take it to a different chip. Okay. So we can see one of our chips over here that has all these different blocks. Maybe these are IPs that were maybe analog or external, maybe some hard IPs, but these are all different blocks that we placed and routed separately, and then we just connect them together by making the routes that go between them in these different routing channels, or there are different approaches to doing this. So what are the disadvantages of doing this? Well, it's much more difficult for full chip timing closure, and I'll discuss in a second what an ILM is. There's more intensive design planning needed. We need to think about how we made this chip from the beginning. We may have these types of feed-throughs. For example, let's say that this is the clock pin, or this is maybe this is a pin that gives a voltage that goes over to here or over to here. So are we going to go around and run around the chip like that, or are we going to go over here where this route actually has to pass through these other hierarchies? So that's kind of called a feed-through. We need to add all kinds of repeaters on such a line to make sure that our voltage, that our signals are passed the right way, and we need to decide on the timing budgeting, which we'll discuss in a second. So what is this time budgeting? So when we were discussing timing, what we said is that our life actually lives in this area. So that's what we know. We know about our flip-flop, and we know that there's an input to our block, and there's some sort of a logic block here, and we know that we want to optimize this logic block according to our constraint. But since we don't know what our actual frequency is or so forth, what we're going to do is often we're going to assume that there's some sort of flip-flop living outside the chip here, and we say that it has some sort of amount of time that it can consume over here until we go into the chip. So how we do that is with an interface constraint such as a set input delay, and that was what we knew before. If this is the border of our chip, we don't know what's going to be connected out here. We have to meet some sort of standard that defines what our hold and setup delays outside the chip are. But when we're talking about hierarchical design, this is we're going to eventually know about this flip-flop, about this logic cloud, and about the skew between the clock nets, because it's going to be the same clock that gets into both places. So what happens is when we combine all of these together, we're going to get this really, really complex model that's going to have, you know, millions of paths and gates and so forth inside. And the thing is that we know that the path from here to here, which was inside our block, we already made sure this met timing. We knew about everything inside here, right? This was a reg to reg path, not an interreg path. So, for example, this path and this path, they're completely taken care of, and it's redundant to check it again once we combine the full chip design. So what we can do is we can actually just take these paths and remove them and delete them, and make a model that just includes these into reg and reg to out and into out paths. That's called an ILM. So that's a type of a timing model that we use for accurate timing of top-level hierarchical design. Okay, another issue is pin assignment. So pin constraints include parameters such as layers, spacing, size, overlap, net groups, and pin guides. What that means is that we have our blocks over here, and we have to decide on the floor plan of each one of these blocks separately, where we're going to actually put the pins, because the pin is just a piece of metal that our final driver or our initial input is going to connect to. So it could be anywhere. It's very different than making the I/O constraints of where these big, huge pads are. It's just a little piece of metal. So how do we decide? And there are two ways. I mean, if we're doing this bottom-up design, for instance, if we made a macro that we're going to reuse in several places, then we arbitrarily, or according to where we want our modules were going to be placed, we scattered the pins in a certain area. But that's not very good, because that puts a constraint on our higher level. If we're actually making, for example, these 4 blocks, what the top level floor planning can do some sort of an initial type of a route and see that there are nets that connect between all these places. So if there are these nets, why don't we line up our pins so the connections are trivial between the 2 blocks? And so we should do that. We can do it with pin guides or all kinds of assignment tools that we have inside the place and route tools. So pin guides can be used to make sure that our pins go to certain areas, and we can align them in a top-down flow and so forth. Feed-throughs. So I mentioned for a minute that there's something about feed-throughs. First of all, if we have channel-less designs or with limited channel resources, or we don't want to route through the channel, we may have this thing called a feed-through, which also makes our life a bit more difficult. So we have some sort of I/O pin, and this net has to go all the way over to this partition C. So what we're going to do is this net doesn't even appear inside the net list of partition A. And this net and this net don't appear inside the net list of partition B. So what we're going to have to do is we're going to have to feed them through partition A and partition B. There are several ways to do that. So we can just push down into the net list ports here and a wire that connects these 2 ports, right? That is one way to do it. Another way is to pre-route this type of a thing, of a net inside the floor plan, and put blockage, make it fixed so it won't be removed. Do that by pushing it down from the top level in it. But there is another problem. Let's say we want to do some sort of optimization, such as adding a buffer inside here. We can't do that. Then we have to push the net down into the net list, and that allows us the possibility of actually, say, buffering one of these nets inside a partition where the net doesn't actually exist. Okay, so that's another kind of a headache that we have to deal with when we're dealing with hierarchical design. So that was all I wanted to say about hierarchical design, and it leads me to the Chip Hall of Fame. So when we're talking about floor plans and even hierarchical design or mini little blocks, one of the most essential attributes of the FPGA is the floor plan, and I wanted to mention the first FPGA, the Xilinx XC2064. And here's a picture of the floor plan over here on the right-hand side. So Ross Freeman, who was the CEO of Xilinx, he bet on Moore's law that it was going to make transistors so cheap that you could waste them. And remember, we looked before at the pad limited type of design where we had a lot of wasted area. Well, Moore's law allowed that to happen because transistors got so small, they're actually really cheap, and sometimes things like routing resources become more expensive than them, or maybe IOs. So Ross Freeman, he bet on that happening. He said we could just put a lot of these types of pre-manufactured gates onto a chip, and we won't use a good large part of them, but it'll be enough, and it'll give us this option of reconfigurability that makes the FPGAs so great today. So it was this chip was released in 1985. It was made in a 2-micron process. It had 64 logic cells and flip-flops and 38 I/O pins. They called it a logic cell array. The program logic was done completely by hand. They didn't have a synthesis or place and route type of a tool such as Vivado or one of the other tools for implementing FPGAs. And another just important point here, that Xilinx was the world's first fabless IC vendor. So now it's kind of given. I mean, you have Qualcomm or Marvell or Apple or Amazon. They're all fabless IC vendors. Only companies such as Intel actually have their own foundry inside their house. Most of the companies we work with are fabless. But in those days, all of the companies had their own fabs. And Xilinx was the first one that actually sent their chip to a different place that had a fab and made it for them. So we'll finish our lecture with a bit about power planning. Let's remember something about power consumption and reliability. So in general, we have dynamic power, we have static power or leakage, and we have the floor plan and the design of the grid. All of this goes into our power consumption and reliability planning. So we have the first problem of average or instantaneous power. So we usually call that IR drop, for I being conductance and R being resistance, or I being current and R being resistance. So IR is a voltage drop, or we have a voltage droop where we actually have these small drops. So IR drop is usually this average power drop. And what we see here is that if the voltage, instead of being this constant VDD that we always assume, it starts to jump around, we can have a point where our cells will fail working correctly. And we have the other thing is a power density problem in the long run, where after using our sending a lot of current through a certain inductor, it can break or short or whatever, and that's called electromigration, or that's usually what we call it. There are different names and different phenomena. So IR drop, as I said, is the drop in the supply voltage over the length of the line. So if we have here some sort of a resistor, an inverter driving some sort of other inverter, and we have some sort of VDD, a power and a ground over here, if we have resistance on the line and we have some current going into here, we get some sort of a voltage drop. And the voltage drop means that our inverter gets VDD minus delta V. In the same way, we have a return path for the current that goes through the resistor, and we have another delta V over here. So what we get is delta V at the bottom of this. Well, we get delta V over here, excuse me, and that means that we'll get some sort of a delta V on the output as well, which will be the input again to our next stage and so forth. So this is a very bad thing to have IR drop. How do we analyze this? Well, what we'll usually do is we'll draw up our whole layout of our power grid of how the power actually gets to each and every gate, and we make some sort of a matrix of the resistances or conductances and the current sources, which are the gates themselves, and then we can solve the matrix and find out for every point on the design what the IR drop is, either in an average case, which we usually call again average IR drop, or on a dynamic basis when there is actually some sort of a vector that changes inside the design, and we see that there are these dynamic things that can happen, especially in a digital design. After you have a rising edge of the clock, everything starts toggling, and that can cause these instantaneous voltage droops to be really bad. Electromigration, which is the other issue of the long-term kind of reliability. It refers to the gradual displacement of the metal atoms of a conductor as a result of a current flowing through that conductor. It's transfer of electron momentum. So the current goes through the conductors and the little electrons hit the atoms that are here, and eventually we can have things break, like over here, or just change their size. We can have hillocks also be created that can actually cut through the dielectric and short two different wires. So there are a lot of things that can happen reliability-wise due to a lot of current running through a small conductor. So this results either in opens, which are a void on a single wire, or shorts, which is bridging between two wires. And even without an open or a short, electromigration can cause performance degradation. So if our conductor here gets thinner, then we have a higher resistance in such a thing. Therefore, we have to solve this by distributing the power in our whole chip. So power distribution has several functions. First of all, it has to carry the current from the pads, the external, the IOs, the pads of the transistor, to the of the chip to the transistors. It's supposed to maintain a stable voltage with low noise. So we want to have VDD, we want to have ground, we don't want to have all kinds of other types of values there, or else all of our static timing analysis will be wrong and our analog blocks won't operate like we simulated. We want to be able to provide average and peak power demands. We want to provide return paths for the signal current, and we have to avoid electromigration and self-heating wear out. So how do we achieve that? We make wider power lines, right? Wider power lines means that we get smaller R, and then the total IR is smaller, so we get less static IR drop, or average current. We get less dynamic, what's called DI to DT drop. So that's because of the large inductances that we often have in the connections from the package to the chip. When we start changing the current suddenly because of like a rising clock edge or something, then we can get this type of a DI to DT drop that also reduces our voltage. And we get less electromigration because we have wider wires. There is a lower probability that an atom will be displaced by being hit by an electron. However, we also want to consume little chip area and wire, and we want to make it easy to lay out so we can deal with it. So these kind of contradict each other. We want to have our cake and eat it too. If we make our power lines wider, we're going to have fewer signals for routing, fewer wires for routing, and we're going to have higher congestion. So what's the challenge of power distribution? Well, let's assume we have a 1 millimeter long power rail in metal 1, and that does make sense since, say, we have a chip and there's some area of the core that's 1 millimeter wide. Well, we have these VDD and these ground rails that will be 1 millimeter long, routed in metal 1 and a pretty small metal 1. Okay, we're given a square resistance. R square equals a typical value of 0.1 ohm to square. Right, so that's our R square. If we make a 100 nanometer wide rail, and let's say we're in like a 28 or a 40 nanometer process, that's a pretty wide, even I would say, wire. So it's not a minimum size wire. What's the resistance of the wire? So once we're given our R square value over here, we can figure out what the resistance is, and it's just R equals R square times the number of squares, which is the length of the wire over the width of the wire, and that comes out to be 1,000 ohms. 1 kilo ohm is the resistance of that wire from side to side. Well, that sounds like a lot. It's for sure not zero. So let's say we have a max current of 1 milliamp per micron. So that's one of the that's what the electromigration guidelines will tell us. Don't have a current over 1 milliamp per micron. So let's say we design our power grid to be at max electromigration. And we have 1 milliamp per micron. What's the IR drop when we conduct this this current through the wire? So the maximum current is 1 milliamp per micron times 100 nanometers. That gives us 0.1 milliamps. So the IR drop is this max current times the resistance of the wire, and that gives us 100 millivolts, which is pretty bad. So what are we supposed to do? Well, we can make the power rails as wide and as thick as possible, and then we get a lot fewer squares, or we get a lot lower resistance. So let's say what we do to analyze the IR drop. We make a hot, like a temperature map of the IR drop around the chip. So this highlights hot spots where the IR drop is bad. And here's an example given by Cadence at one of their CDN lives, where we see this chip that has this area that you can tell there's something wrong here. There's this big hot spot. The IR analysis tool, IR drop analysis tool, tells us that, listen, there's something wrong here. We're getting like really good IR drop all around, and then this area just gets this really bad red area. Well, what do we see? They just added one stripe of metal, and look how much better it got. So that is what IR drop analysis allows us to do, and helps us fix these potentially failure-prone problems. So how do we do this? We need to route power and ground. Every standard cell has power and ground signals. So this is usually a VDD, and this is usually ground, right? VDD and ground. And what we do is we have these rails that are VDD, ground, VDD, right? And that way we can just stick these boxes inside, and we get both VDD and ground inside our standard cell. And that's how we solve this solution of how do we provide VDD and ground to each CMOS gate, which needs both of these power rails. However, we can have that large resistance, as we saw before, going through these long wires. So what we want to do is we want to make the resistance from wherever the power pad is until it reaches each and every gate to be much smaller. And that we usually do with what we call a power mesh. Okay, so what we'll do is we'll often take the power pads that provide VDD from the package. They'll be connected to rings, VDD and let's say ground, something like that. From the package, they'll connect to, say, a ring that distributes it well. They may be several, or there probably will be several of these VDD ground pairs from outside. So we would say we have sort of an equipotential around the chip. Then we'll add these stripes that they connect to these rings, and they can provide the power in a much better way. Usually these are hierarchical, so we'll start from the top. We'll use the top very wide and high wires that have a very low R square, and we'll use them predominantly to connect to VDD and ground. And then as we go down lower, where we need to actually connect to the metal one here that connects then to the transistors themselves, we'll just use some via stacks and some smaller stripes. We'll use a lot of vias between the layers to minimize the via resistance, which can get big. You can imagine that these are huge networks. In general, to make it happen easily, we make these power ground routings very regular, so we can do it with some sort of automatic scripting, and we don't have to really deal with every single wire. We just use some sort of script that puts every certain pitch, it puts another wire, and it makes another via stack, and so forth. So we usually reserve these routing for power ground routing, and we do it early on in the floor plan, and then we can't use this for our signal routing or clock routing afterwards. So how do we do this? The standard approach, as I mentioned before, is what we call a power grid. We interconnect with these horizontal and vertical wires, VDD and ground. Often well over half of the total metal on the upper thicker layers is used for VDD and ground. That's almost the only way that power and ground routing is done nowadays. However, there is another type of an approach, which is called dedicated VDD and ground planes that the DEC Alpha 21264 used. And there you take a whole sheet of metal in a certain plane and use it just for VDD, and another one just for ground. It also causes a lot of good capacitance between VDD and ground, which we want, which we'll see in a moment. But it's really expensive in terms of routing resources and hardly ever done. As far as I know, AMD did it on some of their processors as well. It makes the whole matrix analysis a lot easier though too. So what we should do is we should also co-optimize the power and ground IOs. We should use decoupling capacitors. So what we want to do is, if we have a VDD over here and ground over here, in order to make them less noisy, we want a lot of capacitance between them. Remember, these are DC voltages. They're not supposed to change. To make them change less, we want to put big capacitors to clear out all of those little frequencies. Or in other words, we want to add a lot of charge in between here, so if all of a sudden there's an inverter over here that needs to make a switch, it can take its charge from these local capacitances rather than having to draw them from the main battery. Okay, so that's why we want a lot of cap, as much cap as possible as we can between VDD and ground, and that will we'll add decoupling capacitors wherever we can. We'll just add these extra caps, and the caps it can be in a standard cell that just has like a MOS cap or some sort of other cap in it, and it can also just be by putting a VDD and a ground wire next to each other, and the coupling capacitance is actually good for us. Okay, when we want to go over to multiple voltage and frequency islands, as we discussed before, the power ground problem on clock distributions becomes much more challenging. So how do we create power grids? We're going to trade off IR drop in electromigration versus the routing resources. Remember, the more power we put, the better our IR drop problem and our electromigration problem will get, but we'll have less resources for routing our signals themselves. So we need to make some sort of estimation, figure out what the average current is and what the max current density and everywhere is before we decide how much metal we're going to actually give to the power grid from the beginning. Then we need to build this top-down type of hierarchical approach. We're going to say every single metal, how much of it is going to be power and ground, how many vias are going to connect between the different levels, and so forth. Do we need to have all kinds of things like power gating and multiple voltages? How many power pads actually do we have to have for each voltage? And that depends on how many simultaneously switched IOs we're going to have, which layers are going to be used, what the width and spacing between them are, what the via stacks are, if we're going to have rings around our chip, and etc. If we're going to have some shielding as well. So as you can see here, if this was our whole routing resource, if we use all of this and all of this for power, then that's all we have left for routing. There's going to be a lot on the lower layers and very little room for routing signals on the top layers. We should run an initial power network analysis or an early rail analysis to confirm that what we're doing is right. So just as a kind of a summary about that, blocks with the highest performance and highest power consumption, what we're going to do with them is we'll try to move them close to the edges so their IR drop becomes the lowest, and we're going to move them away from each other. On modern designs, actually, this is all kind of alleviated because we use this approach called Fullchip, where we actually put these connections to the package in the middle, and then we can have direct connection from VDD and from ground to the metal layers that are right smack in the middle of the chip, and that's the main usage of this Fullchip type design, which is much more expensive than a traditional wire bonded design. So as a summary, let's see how we floor plan in our place and route tool. So floor planning is very specific to each design and can include many commands. And you're going to have to always change this according to your specific design, but the general flow or parts of the design is we're going to first initialize our design, which means we're going to have to define all our inputs, our Verilog netlist, our MMMC, which includes the timing, SDC extraction, etc., what our left abstracts are, where our IOs are placed. Then we're going to move over to the specify floor plan stage, where we're going to define our floor plan size, what its aspect ratio is, what our target utilization is inside there. Next, we're going to take our hard macros, we're going to place them inside the design. We can place them in absolute coordinates, or we can use relative placements. We're going to usually define halos and blockages around the macros so we don't bother their pin axis. Next, we're going to define basic regions and blockages inside the chip if needed, so we can define placement regions as we mentioned before, and if we need placement blockages, if necessary, we'd also define routing blockages. Next, we're going to define global nets. So this is a point that we have our design. We decided that our power is called VDD. Let's say this pad over here, we call the net that connects to a VDD, and so we'll have this VDD running all over the chip. But then we have an inverter, and when we look inside the left of the left or the lib of the inverter, what we see is that inside it has a nice inverter here, but it calls this VCC, and this it calls, let's say, VSS, but we called our pin here, we called it ground. So how do we get VDD to connect to VCC? Well, that's what we do with what we call global nets. We say there's a global net called VDD, and all the inverters should connect the VDD to their pin that's called VCC. Remember, when we have multiple power domains, we're going to have something like VDD1 and VDD2, right? And so therefore we're going to say an inverter in here its VCC should connect to VDD2, while this should connect to VDD1. Anyway, that can also get kind of complex, and that's in our UPF, CPF, we can define those things. Okay, next we're going to create power rings. So often we're going to make a ring around the design that is a thick ring that will have VDD and ground that's easy to connect to from the external pad. So if we have a ring around here, it's easy to connect these guys to the ring, and it's easy to connect stripes and so forth to the ring. So it often makes our design much easier if we do that. Okay, next we're going to build a power grid. So we're going to throw down our stripes of VDD and ground across the design, make the different via stacks between them and so forth. Okay, next we're going to assign pins to the design. So that means that we have to decide where our peripherals will sit. If we have our VDD, if we're at the full chip level, of course, that's going to be defined by the I/O placement. So that's it for our discussion of floor plan. It was a bit higher level type of a lecture, but it's really something you have to do. You have to gain experience from. You have to do a lot of trial and error, see how our routing congestion becomes, see how our placement comes out, what kind of timing we can get. And this is something you'll have to go through many times. Floor planning usually takes up a large part of the design time of a back-end designer.